The first thing I want you guys to focus on now, because now we got to play the catch-up game, and obviously this is the class before spring break and stuff. So I am buying you guys a little extra time. So let's go over here to our modules and scroll down and take a look at what we got. And also, by the way, Katrina will be back here in just a few minutes. I have your homework number ones. I've had them for a while. Problem is, I never could find a good time to pass it out to you because we're either turning in your homework number twos or focusing on to test material and stuff like that. So, and I haven't posted them onto your Canvas site yet. That's just me got to get the Excel spreadsheet stuff merged up here. But I will probably by tonight or tomorrow. I do have that thing coming back to you guys for another homework set. But where are we at right now? We just had our test number 2, which is at the end of section 2.8. And so here we go. Now, let me describe to you what's exactly going on and stuff like that. So we're now entering into chapter 3. Chapter 3 is about exponential and logarithmic functions. Now, we know as a prerequisite to the course, everybody in here has taken, exponents and logs. You may not remember much on the logs, but we took logs and all those properties of logs and the property of exponents and the like. So, what we have done, because there's two focus if you read your textbook. They're doing an algebra review focus on reminding you about the exponential and logarithmic functions and what you can do with those things. And then we're going to start playing around with limits, with the eventually trying to get into taking the derivative of exponential and logarithmic functions. So this is still calculus, so we're going to take a derivative of somebody. So right here at the beginning, this is what we decided to do. This is part of that redesign thing that because the review of algebra like logs and trig and in this case exponentials and the like, that's review. We're not supposed to actually cover that in class. But because I have, literally 10,000 students each semester, I have 10,000 different backgrounds with this material. So some folks have a very strong algebra background with this material. Some folks, my teacher didn't emphasize logarithms or trig or something like that, and I don't have as strong a background. So what I did was I made 2 videos covering 3.1 and 3.2. So when you actually go to your notes over here, this right here, I called it Chapter 3 Review, Section 3.1, 3.2 Logs. This is all about review, about one-to-one functions, finding inverses, and then flipping over here to talking about different types of inverses, talking about the idea of switching the x and y coordinate to the exponential function. And the reason why we talk about inverse is because logarithms are the inverses of the exponential. So we're setting you guys up for all this stuff. So we talk about exponents, we talk about logarithms, and all this material that I actually covered for section 3.1, 3.2 stuff is actually all the way up from page 87 through 95. I actually did in these 2 videos. And here are the videos for you guys right here. This one is section 3.1, 3.2. I called it part 1 and part 2 because I actually was an old semester. I actually covered this thing in class. But when we came up with the redesign aspect of the course, this was supposed to be review. So you're supposed to make sure you know it, but it's not something we're actually supposed to cover in class according to our syllabus and stuff. But so to make sure you know it, please watch the video and take notes off of it and fill them out, because the notes that I'm doing that I printed out for you guys here is actually what I did on the video. But it's review. So, and then we come over here to section 3.1 again. Because what we did was we removed all the review material and made it separate as some notes. And now we're going to start talking about limits and then eventually the derivative stuff here. And that's what I'm actually covering on today. Now, if you look, because we just had our test, and I am trying to buy you guys some extra time for that hiccup system, when is quiz 3.1 actually due? Pre-section quiz. March the 13th. And what day is that? It's the day we get back from spring break type thing here. Does that make sense? And 3.1 and March 13th, 3.2, both these things will be due then. If you haven't done them, don't worry about it. You got time, but don't wait till the last minute type thing here. Also, let you guys know, yes, you do have homework over spring break because it's a college thing here. And I kid my students about this, but it's true. What's the purpose of spring break? Give me a break. No, it's to get you to catch up. That's the purpose of spring break, is the chance for you guys to catch up. Now, you guys are freshmen, sophomore, you may not have as much catching up to do, but trust me, by the time you get to be juniors and seniors in grad school, oh, you're so far behind on everything that you're just going to beg for spring break just to get caught up. So, you know, for most folks, Cancun and Cozumel and hanging out at on a cruise, not much of an option. So if you got to go on a cruise, enjoy it your freshman and sophomore year. By the time you're a junior or senior, you don't have time for that. You got too much work to do. So just to let you know what your future is going to entail. So there you go. So let you guys know, catch up. But so that being the case, you know what your job is to do over spring break? Watch these awesome videos, take notes off of it, and guess what? You got web work on it. This is the web work review on logs and exponents. It is due on November the 11th. What day is November the 11th on? Let's go to the calendar. Yep, that's right. March the 11th. I'm sorry, I'm thinking following. March the 11th, which is due. Sorry, hold on. Okay. Thank you for attacking me. Jeez. So the 11th, which is due this Sunday before we get back from spring break. Does that make sense? I'm just trying to point these deadlines out to you guys and stuff like that. But we are a little bit ahead of the game, but this is what you need to do because this is review. I'm not actually supposed to cover this in class, but I did make some videos for you guys just to make sure that if it's been a while since you've seen exponentials and logs, you can get caught up so you can make sure that you just ace the web work, stuff like that. And then when we come back, you got section 1.3 and 1.4 to do, and I'll start covering that stuff today. And then we'll get back into our regular schedule and then back to our normal stuff. So this is the game plan. So you know, right after I give you guys a test, I always allow for a little bit of adjustment period and buy you some extra time to get us caught back up on a pattern is my big goal here. So all right, so let's go ahead and get started. So, like I said, Katrina, also you brought in those papers and she's passing them out, so they're arranged somewhat alphabetically, so grab your paper and just pass it on. This was homework number 1, and hopefully I'll have homework number 2 for you guys probably right when you guys get back from spring break. All right, so all these papers, this is the review part, and then we're going to come back and look at exponentials and logarithms from a calculus perspective. So here we go. Section 3.1. Now hopefully you watched the awesome pre-section video already and taking notes off of it and passed the quiz, but here's the idea. What exactly is an exponential function? Let me give you a little background. An exponential function is a function where the variable is in the exponent. So you have something like y equals a raised to the x, where a is a constant. But here's the deal about constants. Those constants have got to be either a fraction, somewhere between 0 and 1, or they're going to have to be bigger than 1. For you see, 1 raised to any power is 1. That's not real exponential here. So you either got to have a fractional base, but it's got to be a positive base, or the base has got to be bigger than 1. And so when you look at these things, you understand this is going to be, again, application stuff here. So when I look at these things, do you know what a graph, when you have a fractional base of y equals a to the x looks like? It looks like this. It goes through the point 0, 1, but as you get higher and higher powers, when you take a fraction and raise it to higher and higher powers, you get smaller and smaller and smaller. This is what the function looks like. But if your base is bigger than 1, it goes through the point 0, 1, but as your base is bigger than 1, when you raise a number bigger than 1 to a power, it continues to blow up, and you get this picture over here. So this is your exponential function, y equals a to the x, with the base being bigger than 1. And we tell you this because, you know, we expect you guys to know basic rules. You know, when I say, think of a quadratic, what's the first thing that pops in your mind? Quadratic. A parabola, U-shaped looking graph. If I say, what does a square root of x graph look like? Starts at the origin, bows out. You know these basic pictures. These are the basic pictures of your exponentials. Now here's the big deal. We have two different kinds of exponentials. When the base is a fraction versus the base is bigger than 1. The one that when it's a fraction, we call this a decay graph. As time goes on, you get smaller and smaller amount. When the base is bigger than 1, that's called a growth graph. As time goes on or x gets bigger, the graph gets bigger and bigger and bigger. This is a growth model. This is a decay model. So you're going to see a lot of modeling with this type of material. Okay? So, now, in terms of analyzing these guys, rules of exponents. So we're talking about limits here. The first rule of limits is always plug in a number. So if you take the limit as take the limit as r approaches x of a to the r, you get a to the x. First rule of limits, plug it in. Replace r with x, you get a to the x. So first rule of limits, if you're doing limits even on exponentials, plug in a number. Okay? Now, here's the deal. Because of these two graphs up here, when I take the limit as x approaches infinity, when I have a base that's bigger than 1, the base is bigger than 1 is going to be this graph over on this side. When you've got a base bigger than 1, and you take the limit as x approaches infinity, the thing's getting bigger and bigger and bigger, you're going to get infinity out of it. However, when you take the limit as x approaches negative infinity, this thing horizontals out and gets very, very close to 0. So we say the limit goes to 0. These are the extreme values of the exponential when your base is bigger than 1. When your base is a fraction, you have a flip-flop. When you take the limit as x approaches infinity of a fraction, you know, it's the old kind of the concept of taxes here. You know, the government takes, what, about 40% of my money in taxes. So they take 40% this year, they take 40% next year, they keep taking 40%, 40%, 40%, 40%. Eventually, guess how much money I'm going to have? Nothing. Here's the thing. All right. Here's the idea behind taxes. All right, so let's say they take 40%. So let's say I earn $5. That would be very close to my salary. But yet the government takes 40% of my salary, which means I get to keep 60%. So out of my $5, I get to keep $3. You with me? But then they're going to take another they're going to take another 40%. So I got now $1.8. Okay, and I keep going on forever and ever and ever and ever and ever and ever and ever. And guess what happens? I got a penny, and maybe a little bit less than a penny, and eventually I'm going to owe somebody. Okay, does that make sense? Well, that's not how taxes really work, but almost when you actually start having to pay taxes, because you feel very defeated when you actually, every dollar I make, I get to take home 60 cents. So 40 cents of it goes to somewhere. God knows what the government does to it, not much anyway. But you get the idea. This is the idea of taxes. But what the goal is I'm supposed to make more money next month, or at least the same amount of money next month, so they can go take another 40% of that. But eventually, it's this fighting game that you just can't ever win, because every time you turn around, you know, it's April 15th, just around the corner, and I'm working on my taxes, and every time I do, I get angry. So, you know, there's a huge difference between gross and net. You know what that is, right? It's basically how much money I should have, but I don't. Okay, that's my difference between gross and net, and it gets larger every year. But nevertheless, this is important because mathematically we can model these type of things to understand what exactly is going on and stuff. Okay, I remember, like I said, I remember my first paycheck when I worked at Burger King. That's right, I worked at Burger King when I was in high school, just before I went to college. You know, because I'll get you guys to know a good story here. I'm from Rocky Mountain, North Carolina, so this is a real North Carolina accent around here. So I actually understand your woes, because I came from a North Carolina public high school myself. So I understand. And I remember, you know, what did we do in Rocky Mount when we graduated high school? we went to the beach for a week. All your friends, your senior day here. And I came back home from the beach, and I was sitting there in front of the TV. And my dad came in there and said, "Boy, what you doing?" I said, "Watching TV, Dad." He said, "No, that's not my question, son. What are you going to be doing this summer?" Well, I thought about it for about 10 seconds and said, "Watching TV, Dad." He said, "Not on my couch, you're not." And I heard those awful words a son should never hear from his dad. Get a job. My first job I ever got was in construction. I dug ditches. I weatherproofed houses. I put sheetrock in. I helped wire the thing. And now you guys know in North Carolina, I worked June, July, and August. That's right. Shake your head. Miserable. Miserable. 120 degrees in the shade. And this is eastern North Carolina, so 120% humidity too. It was absolutely awful. And in that summer, before I went off to state, my dad called me in and said, "Son, how did you enjoy that job?" I said, "Dad, I didn't. Boss man yelled at me every day. I couldn't do anything right. I'm 18 years old, so when everything went wrong, it was obviously all my fault. The wiring's wrong because I did it." "Oh, I didn't. I just pulled wires, man." But whatever. It was still all my fault. I got yelled at all the time. It was 120 degrees. I lost 5,000 pounds in just sweat alone that summer. And he said, "Did you learn something? This is why you want to go to college. So you don't have to do this job the rest of your life." You're right. It's nice in my office because it's comfortable when the air conditioner's working and when the heat's working on a day like today. It's nice. It's called a career. This is why you guys are in college, to study, to learn something or other, so you can have not just a job. You can get a job right now if you want one. But you get a career. And again, I'm motivating you on why you want to study this stuff. This is key, so you can have a career with this material. So, and I give this to motivate my students every semester about this, but it's about spring break time. Semester's about half over. Now's the time for me to get you guys motivated again of why you want to be here. You want to graduate so you can get not just a job, a career. Remember that. So, when you study this stuff, please keep that in mind and motivate yourself to even work even harder with this material. All right. So, if my base is bigger than 1 and I take the limit as x approaches infinity, I get infinity. When my base is bigger than 1, I take the limit as x approaches negative infinity, I get 0. If I have a fractional base, when I take the limit as x approaches infinity on a fractional base, a fraction of a fraction of a fraction gets smaller. That goes to 0. But if I take the limit as x approaches negative infinity on the fractional base, that actually blows up to infinity. Now, the other aspect of this stuff is this. When you study exponentials, there is one of these God-given numbers that you just run across when you study science. And that number is E, 2.71828. There's other numbers that we focus on in terms of what we call God-given numbers, and that's when you study circles. If you take any circle, you take the circumference of the circle and divide it by the diameter of the circle, whether it be a big circle or a small circle. You know what number pops up? Every time. 3.141592669, the irrational pi shows up every time. Another one of these numbers that shows up every time is this very strange number E, 2.71828. It's irrational. It keeps on going forever. And you're going to understand why this number is so important when we start studying science pretty much in the next 2 sections. I'm going to actually go back to this guy. But this E, which I no doubt you've seen before, it comes when you take the limit as x approaches 0, and officially this is supposed to be on the plus side. Take the limit as x approaches 0 on the plus side of 1 plus x raised to the 1 over x. When you do this, you get E, 2.718 every time. And so with this E, which is 2.8, I just had it in my head and I can't remember it. To E raised to the first power. 718. Thank you. 2.71828. ... This E number is a bigger number that is bigger than 1. So when you actually look at the exponential, the graph looks like this of y equals e to the x. And because of that, when I take my limit as x approaches infinity of a number bigger than 1 raised to the infinity, I get infinity out of it. And when I take the limit as x approaches negative infinity of e to the x, this thing goes to 0. So this is, again, a very important concept here, because this model of e to the x is, we're going to see this a lot. Now, again, part of the review, and I'll go over this because we got time, which I did on the pre-section videos, is solving exponential equations. There's two ways to solve exponential equations. Now, one thing you need to remember, and again, I'm focusing on it as a review, is this. When I'm trying to solve for exponents, there's only one thing in the universe that brings down exponents. This is why it was derived and discovered. It's called logarithms. Logarithms solve for exponents when you need it. So in this first problem, I've got 3 raised to the x is equal to 1/9. This one's special that I don't actually have to go through logs to get this particular problem. I could if I wanted to, but I can clean this guy up. I can write it as the same base. What exactly is 9? Break down 9 for me, please. It's 3 squared. So this is 3 to the x is equal to 1 over 3 squared. But then I can use my property of exponents, and that's a part of that big review from 3.1, 3.2 we were talking about. To bring stuff off the bottom to the top, what do I got to do with the exponent? Make it negative. So this gives me 3 to the x is going to be equal to 3 to the negative 2. And here's your rule of thumb when it comes to exponentials. If you can write the exponentials with the same base, if the bases are equal, that forces the exponents to be equal. So the exponents implies that x has got to be equal to negative 2. Does that make sense? Solving for x, x is negative 2 here. But what about this one? I got 8 raised to the 4x plus 1 equals 3. The problem with this guy is I can't write these guys as the same base. Now I could break down 8. 8 is 2 cubed. That's great. I can write this as a base 2, but this is 3. 3 is not 2 raised to any power that I know of or anything else. So they're not the same base. Does that make sense? When you cannot write them in the same base, there's only one thing in the universe that solves for exponents, and that's logarithms. Now, just to remind you, on your calculator, there are 2 log buttons on your calculator. There is the LOG button and the LM button. What's the difference? The LOG button is what we call the common log. It is log base what, even though you don't see the base down there? Base 10, common log. And the LN button, it's called the natural log, is actually a log base E, that 2.718 number. You know, but this one's used so much in science, we gave it a special log. Okay? So on this particular problem right here, if I was going to do this one and calculate it by hand, I would do this. I would take the log of both sides. And since I don't see an E in this problem, I'm going to use the common log. Well, honestly, it won't matter. You can use either log you want to. So I take the log of one side. Log of 8 raised to the 4x plus 1 is equal to log of 3. Now, again, part of that review that we wanted you to go over before we talked about today is log properties. With log properties, there are, 7 major properties you guys need to know. Okay? And tell you what, I'll just flip this thing over and let's talk about your log properties for just a second. What are my log properties? My log properties are these. The log base A of m times n. You know how to clean that up? Because logarithms solve for exponents, and because when I have exponent raised to a power, like powers, you basically turns into addition. This becomes log base A of m plus the log base A of n. I'll explain why in just a second. All right, log base A of m divided by n is the log base A of m minus the log base A of n. And the log base A of n raised to the c equals c log base A of n. And these are the big 3 log properties here. Let me explain why. Logarithms are the inverses of exponentials. That's what that chapter 3.1, 3.2 review is all about. Do you guys remember your exponential properties? A to the m times a to the n. Multiplication, like bases, what do I get to do with the exponents? You add them. Like bases, division, a to the m divided by a to the n. If the multiplication turns into addition, what does division turn into? Subtraction, a to the m minus n. And the last one, a to the m raised to the n. A power raised to another power, what do you get to do with the powers? Multiply. But since logarithms are the inverses of the exponentials, here's the deal. Each one of these guys has its own respective log property. So when you multiply like bases, I add the exponents. Logarithms solve for exponents, so this idea of log base a of m times n is the same thing as log base a of m plus the log base a of n, because you basically add the exponents, and logarithms solve for exponents. Division turns into subtraction of the exponents, and power raised to another power, you get to multiply, but to multiply, you have to put the constant out front. It's these three properties written in log format. The other log property you need to know is the definition. Because here's the deal. What grade did you guys start learning about exponents? What grade was exponents first taught to you guys? You know, 2 squared is what? 4, things like that. It should have been around the 4th grade, because powers were, you know, a way of multiplying fast. 2 squared, that's 2 times 2, I get 4. You know, 2 cubed, it's 2 times 2 times 2, that's 8. Powers were a fast way of multiplying. We did that in the 4th grade. What grade was it that you first discovered the logarithms? Depends on students, but most people, 10th or 11th grade is when you really started studying logarithms, okay? So you've been studying exponents since the 4th grade, but you've been only studying logarithms since the last few years of high school. Does that make sense? And because of that, logarithms are still concerning to a lot of students because you haven't had that much time with them. Here's the deal. If you have y equals the log base a of x, this is equivalent in saying a raised to the y equals what you're taking the log of x. This is called the definition of logarithms. And I call it the smiley face definition because here's the deal. If you don't like the log equation, you always have the ability to rewrite it in its exponential form. These two guys are synonymous. They're the exact same thing, but this is where most people understand it. This is just written in log form. So if you ever got a log form, you can always rewrite it. And here are the, like I said, here are the other properties coming from the exponentials. The others, I said there were 7 properties here. These are the big 3. 1, 2, 3. Number 4 is this. What is the log base a of 1? In other words, a raised to what power equals 1? What can I raise any number to what power is going to give me 1 out of it? 0 power. Property number 5 is this. The log base a of a. What do I need to raise a to get a back again? The first power. Anything to the first power is itself. Property number 6 is this. A raised to the log base a of x. Exponentials and logs are inverses. Inverses mean they're going to cancel each other out. They cancel each other out, you're left with x. And similarly, property number 7, you have this log base a of a raised to the x. As long as the base on the log and the base on the exponential are the same, they're going to cancel, and you're left with x. These are the 7 properties of logarithms with the definition. Okay? So, back over here. With this problem, I got 8 raised to the 4x plus 1 equals 3. Because the variables in the exponent, I took the log of both sides. And I took log base 10. Now, according to my log properties, where do the exponents get to go? Out front is a coefficient. So I get 4x plus 1 equals the log, times the log of 8 is equal to the log of 3. Now go solve for x. How would I solve for x on this thing? Well, what gets rid of multiplication? I would divide both sides by the log of 8. This gives me 4x plus 1 is equal to the log of 3 divided by the log of 8. Now what do you got to do to solve for x? Subtract 1 and then divide by 4. So this is going to give me x is equal to the log of 3 over the log of 8 minus 1 divided by 4. It's a crappy number, and I'll show you what that number is. It is parentheses around your numerator, log of 3, close parentheses, divided by the log of 8, close parentheses, minus 1, close parentheses for the numerator, divided by 4 in the denominator. The answer is negative, oh, sorry, you guys can see this, negative 0.1179197916. You don't believe me? I can do this. Let me sit there and store this under X or something like that. If I go back and plug it in here, right now, every time the calculator sees X, it sees this number here. If I take 8 and raise it to the 4X plus 1, you know what I should get? 3, and I do. This is the value of the X that actually solves it. Does that make sense? But there's more review of this stuff. Here's one. Starting with the graph of f of x equals 9 to the x. Write the equation of the graph that results from shifting the f of x 9 units upward. They're still trying to remind you guys of the techniques of shifting, stretching, and reflecting. So if I want to move a graph 9 units upward, what do I got to do to that graph? Just add 9 to it. You know, this is called a vertical shift. Put it into the problem. So the answer is y is equal to 9 to the x plus 9. That plus 9 moves it 9 units upward. Part B is they want you to shift f of x, which is 9 to the x, 7 units to the right. Here's your problem. When you go left or right, that's called the horizontal shift. And it has the effect on where the x is on the original function. This is 9 to the x. And it has an opposite effect. So here's the deal. If I want to go 7 units to the right, I'm going to put this 7 stuff up where the x is at. But right, you always think of positive, but it has the opposite effect. I'm going to put x minus 7 where the x is at. So I get y is equal to 9 raised to the x minus 7. That has the effect of moving it 7 units, the graph of y equals 9 to the x, 7 units to the right. Does that make sense? Now, what about reflecting? To flip a graph upside down, you make the graph negative. Okay? So here we go. I want you to reflect f of x about the x-axis. About the x-axis means I'm going to flip it upside down, right? And all I got to do is make the function negative. So y equals negative 9 to the x. But this is the deal. What does that negative actually stand for? Negative 1 times. Now, this is important because of order of operation. What is your order of operations? Number 1, you always do what? Inside parentheses first. Number 2, then what? Exponents. Number 3, then what? Very good for the one person that said it. Multiplication, division from left to right. Multiplication doesn't come before division. It's always multiplication, division from left to right. And then the last step is addition, subtraction from left to right. Okay? If you wanted to order to them, you go back and put parentheses around it. So if I got a bunch of things being added or subtracted, you always work from left to right on that thing. Okay? And again, I will show you an example here, down here. I had a question for you guys. Y equals 3 times 2 divided by 6 times 3 plus 5. All right. Without the use of a calculator, tell me what the answer is. All right, I hear two numbers. I hear 6 and I hear 8. Okay? Do I hear any other ones? All right. A lot of people tell me this. 2 times 3, that's 6. Divided by, what's 6 times 3? 18 plus 5. 6 divided by 18 is, what, 1/3? Because 6 goes 18, 1/3 plus 5. The answer is 5 1/3. Or for you, that would be 15 16/3. Right? Wrong. Because, and again, what I'm telling you this is because I've seen teachers, elementary school teachers, mess this thing up. Because they somehow were taught that multiplication comes before division. That ain't right. If you want multiplication to come before division, you got to put parentheses around some stuff. This is actually wrong. The real answer is this. You run it from left to right in a string. What's 3 times 2? Divided by 6?
1.
Times 3? That's 3 plus 5. The actual answer is 8. You run it from left to right. Multiplication does not have priority over division. You just run it from left to right. But it's this type of mess that makes people get very leery of mathematics because they think, well, which rule is it? No, there's only one rule. This is something made up. And I think it came from someone trying to come up with the mnemonic. Have you ever heard of the please excuse my dear Aunt Sally mess? What does that mean? Please excuse, what's that? Parentheses, exponents, my dear, and that's where they screwed it up there. It's actually multiplication division from left to right, but somehow they always thought multiplication must come before division because of the my dear thing or something or other. But no, it's just multiplication division from left to right and then add subtraction from left to right. So again, this is a review section here. So here's the thing. When I look at a problem like this is -1 times 9 to the x because of order of operations. You have to raise the 9 to the x first and then multiply by -1. You don't multiply first. This is not -9 quantity to the x power because there's no parentheses here. It's 9 to the x because exponents come first and multiply by -1. That flips it upside down. What's the domain? F of x is equal to 16 divided by 1 minus e to the x. Well, it's a fraction, a rational expression for you fancy folks. What does that mean? I can't divide by what? 0, which means that 1 minus e to the x cannot be equal to 0. Solve for x. I would add e to the x on both sides, and I get 1 cannot be equal to e to the x. What gets rid of an e so I can bring down the exponent? You remember, natural logs. It's a log property. The natural log of e to the x, natural log is log base e of e to the x. The natural log and e's cancel, you're left with x. So you take the natural log of both sides. Natural log of 1 cannot equal to the natural log of e to the x, which means x cannot equal to the natural log of 1. But what is the natural log of 1 equal to? In other words, e raised to what power is equal to 1? 0. X cannot be equal to 0. The domain is all real numbers except 0. That's what it asks for the domain. We would say -infinity to 0, union 0 to infinity. You can have anybody but 0. What about the other dude? What about g of x equals 16 divided by 1 plus e to the x? What's the domain? Well, again, I got the same problem. This 1 plus e to the x denominator cannot be equal to 0. Solve for x. I'm going to subtract 1 from both sides, and I get e to the x is equal to the natural log of -1. So, screwed that up. E to the x equals -1. And then I got to take natural log of both sides. The natural log and e's cancel, so x cannot be equal to the natural log of -1. But what is the natural log of -1? Log properties. Non-real answer. You cannot take the log, any log, of 0 or negative numbers. You can only take the log of positive numbers. This thing does not exist. So the domain is actually -infinity to infinity, all real numbers. Again, trying to remind you of your log properties. When it comes to logarithms, you can only take the log of positive numbers. You can't take the log of 0, nor can you take the log of negative numbers. Here's a web work problem for you guys. Find the exponential function f of x equals c a to the x, whose graph goes through the point 0, 5 and the point 220. All right, so I got a function. F of x is equal to c a to the x. You first start with your first point, which is 0, 5. So when x equals 0, y, or the function, equals 5. Plug it in. So 5 would be equal to c e to the x 0. C times a to the 0. What is a? Any number base, got to be bigger than 1, raised to the 0 power. What's anything to the 0 power equal to? 1. So this tells me c is equal to 5. Does that make sense? And therefore, you have the function f of x is equal to 5 times a to the x. Now you're going to plug in the next point, 220. X is 2, y is 20. So 20 would be equal to 5 times a squared. Solve for a. I would divide by 5. That gives me 4 is equal to a squared. And what kills off a square? Square root. So what's a equal to? Plus or minus, or just 2? Now remember, bases have to be strictly greater than 0. You cannot have a negative base. So you would take the positive square root only. A would be 2. Therefore, your answer is f of x would be equal to a, c, which is 5 times a, which is 2, raised to the x. There is the answer to the problem that goes through these 2 points. All right. A little side note. I talked just briefly about exponential limits. I'm going to give it to you in shorthand notation, but this is important because not only do we do it here, we're going to beat it to death again in Calculus 2 and in Calculus 3. It's going to come back and haunt you. Here's the deal. E to the infinity. E is 2.71828. When you raise it to the infinity, you get infinity. However, e to the negative infinity, negative exponents go on the bottom. This is 1 over infinity. 1 over infinity is 0. These are your properties, the limit properties I did a few minutes ago, just rewritten for you guys. So, first rule of limits is plug it in. What is the limit as x approaches infinity of 3e to the negative 2x? This would be equal to 3e to the negative 2 times infinity. Order of operations. Work it out. What is negative 2 times infinity? Negative infinity. So this is 3e to the negative infinity. Does that make sense? But what is e to the negative infinity? What does that equal to? 0. So this becomes 3 times 0. So the answer is 0. Does that make sense? Questions? Okay? Look at the next one. Plug in infinity. This gives you 3e to the infinity divided by 5e to the infinity plus 12. What's e to the infinity equal to? That's over here, one of our properties we have memorized. E to the infinity is infinity. So this will be 3 times infinity divided by 5 times infinity plus 12. 3 times infinity is infinity over 5 times infinity is infinity plus 12 is infinity. And what exactly is infinity divided by infinity? It's indeterminate. You can't tell. So there's a trick to this one. The trick is to do this. You got the limit as x approaches infinity of 3e to the x over 5e to the x plus 12. Well, you remember way back when in chapter 1.6, when you had the infinity over infinity, you multiply by 1 over x to the largest power, the degree of the denominator. Well, this one, you don't have a denominator, but you do have an exponential. So you multiply by the commander, which is at e to the x. What I do to one side, I do to the other. I'm going to multiply both sides by 1 over e to the x. It's a ratio of 1, which doesn't change my problem. So this is equal to the limit as x approaches infinity of 3 times e to the x times 1 over e to the x. E to the x cancels. You're left with 3. 5 times e to the x times 1 over e to the x. When I distribute, this e to the x cancels, so you're left with 5 plus 12 divided by e to the x. Now, plug in your infinity. So this would be equal to 3 over 5 plus 12 divided by e to the infinity. What is e to the infinity equal to? Infinity. So this is 3 over 5 plus 12 over infinity. But wait a minute. This is one of our our exponential properties from chapter 1.6. When the denominator goes to infinity, the overall fraction goes to what? What's 1 over a billion? A billionth. What does it go towards? 0. So you're left with 3 over 5. That's just 3/5. Does that make sense? Questions? Yeah, but we're playing around with the exponents. But you got to pay attention when the base is bigger than 1, when the base is a fraction. Based upon that, do problem number 8 here. What is the limit as x approaches infinity of 0.77 to the x? This is 0.77 to the infinity. But what you should focus on is the base is 0.77, which means that is a number between 0 and 1. And so when you have a fraction and that's being raised to a power, what's 77% of 77% of 77% of 77% of 77%? Eventually, what's this thing going down to? The answer is going to be 0. Because the base is a fraction, so when you raise it to the infinity, it goes to 0. A fraction of a fraction of a fraction of a fraction, eventually you got nothing. Number 8, again, one of these guys, follow your nose. What is the limit as x approaches infinity of e to the negative x squared? You have to follow your nose. Rule of thumb is to plug it in. This would be e to the negative infinity squared. According to order of operations, what am I going to do first? Inside parentheses, I got infinity. What comes next? Exponents. What is infinity squared? Infinity. And then you leave the sign there, because it's a sign. So this will be e to the negative infinity. Does that make sense? Because you got to square it first. Order of operations. Infinity squared is infinity, and then negate that. And this is a rule. What's e to the negative infinity? It's one of our rules. What is that? That's 0. Why? Because remember, e to the infinity is infinity. E to the negative infinity is the same thing as 1 over e to the positive infinity, which is 1 over infinity, but infinity in the denominator makes it go to 0. So those are my patterns that you need to know about these e's. This is what chapter 3.1, the calculus part, is all about. Look at this one, number 10. I want you to evaluate the limit as x approaches infinity of e to the 5x plus e to the negative 5x divided by e to the 5x minus e to the 5x. All right, first rule of limits, plug it in. This will be e to the 5 times infinity plus e to the negative 5 times infinity over e to the 5 times infinity minus e to the negative 5 times infinity. 5 times infinity is infinity. So this is e to the infinity plus negative 5 times infinity is e to the negative infinity over e to the 5 times infinity is infinity minus e to the negative infinity. But e to the negative infinity is 0. E to the infinity is infinity. So this is infinity plus 0 over infinity minus 0. Infinity divided by infinity is indeterminate. You can't tell what's going on here. But I showed you guys the trick just a few seconds ago. When you get one of these infinity over infinities with these exponentials, you multiply by 1 over e to the highest power of the exponent, if you will. So here's the thing. Here's what you should do. This will be equal to the limit as x approaches infinity of e to the 5x plus e to the negative 5x over e to the 5x minus e to the negative 5x. What has the largest power in your denominator? Is the largest power a 5x or a negative 5x? Positive 5x. So multiply by 1 over e to the 5x. What you do to the bottom, you do the top. Do the denominator, do the numerator. And distribute. This is equal to the limit as x approaches infinity of, here we go. What's e to the 5x times 1 over e to the 5x? You get 1, because e to the 5x cancels. Okay? Plus, what's e to the negative 5x times 1 over e to the 5x? And when you divide, you subtract exponents. So what's e to the negative 5x times 1 over e to the 5x? We'll subtract exponents. What's negative 5x minus 5x? E to the negative 10x. When you multiply, you add exponents. When you divide, you subtract exponents. Top minus bottom. Divided by e to the 5x times 1 over e to the 5x is going to be 1 minus e to the negative 5x times 1 over e to the 5x. When you divide, you subtract exponents, and it'll be e to the negative 10x. Now, plug in your infinity. This is equal to 1 plus e to the negative 10 times infinity over 1 minus e to the negative 10 times infinity. What is negative 10 times infinity? Negative infinity. So this will be 1 plus e to the negative infinity divided by 1 minus e to the negative infinity. And there you go. What's e to the negative infinity equal to? Things we remember, what's it equal to? 0. So this will be 1 plus 0 over 1 minus 0. And pretty much 1 over 1. The answer is 1 to this problem. It's equal to 1. Does that make sense? Here's one. What is the limit as x approaches infinity of e to the negative 2x times the cosine of x? Well, first rule of limits is plug in a number, but you're going to have a problem there. Because you're going to get e to the negative 2 times infinity times the cosine of infinity. And what is the cosine of infinity? It's called divergent. Because cosine is a wave. It bounces between what two numbers? Cosine of x, negative 1 and positive 1. So what I'm going to do here, because we know that the cosine of x always bounces between negative 1 and positive 1, we're going to use that thing we did before, which was called the squeeze theorem. So, the limit as x approaches infinity of e to the negative 2 times x times negative 1 is less or equal to the limit as x approaches infinity of e to the negative 2x times the cosine of x, which is less or equal to the limit as x approaches infinity of e to the negative 2x times positive 1. All I'm doing is replacing cosine on the left with negative 1 and cosine on the right with positive 1, because the cosine of x is bounded between negative 1 and 1. So now, do this problem here. What's the limit as x approaches infinity of e to the negative 2x times negative 1? We'll plug it in. You get e to the negative 2 times infinity times negative 1. Well, 2 times negative infinity is negative infinity. E to the negative infinity times negative 1 is negative that. But what is e to the negative infinity? Well, these rules you have memorized. What is it now? 0. This part goes to 0. What about this guy over here? Plug it in. I get e to the negative 2 times infinity times 1. But 2 times infinity is negative infinity, and e to the negative infinity times 1 is 0. So the left goes to 0, the right goes to 0. By the squeeze theorem, what's the limit as x approaches infinity of e to the negative 2x times the cosine of x. What's that going to equal to? If the left goes to 0 and the right goes to 0, the middle's got to go to 0. Start the squeeze there. Does that ring a bell? Section 3.2. Section 3.1 was about exponentials and logs. Section 3.2 is about logarithms and limits. Okay? 3.1 is about limits. It's focusing mainly on exponentials and a few logs. So here it is, and I've rewritten those formulas for you guys. Here's the deal. This is the graph of what y equals the log base a of x looks like as long as the base is bigger than 1. It looks like this guy here. And we have the expansion stuff here. Log base b of m times n is equal to log base b of m plus the log base b of n. Multiplication turns into addition. Log base b of m divided by n is equal to log base b of m minus the log base b of n. Division turns into subtraction. Log base b of m raised to the n, power raised to a power multiplied of n times log base b of m. Okay? So, here we go. This is a review from the review section of this chapter. For the function f of x equals 3x plus 1 over 2x plus 4, what's the inverse function going to look like? You guys remember how to do inverse functions? Step 1. Graph the thing. Over here at negative 2. Over here at 3 halves. This is what the graph looks like. The question is it 1 to 1? You remember how to check for 1 to 1 functions? Now, the vertical line test checks for functions. The horizontal line test tests for 1 to 1 functions. Because only 1 to 1 functions have inverse functions. Again, what part of the 3.1, 3.2 review was about. Any horizontal line only intersects at once. This thing is 1 to 1. Check. Step 2. Replace function with y. I get y equals 3x plus 1 over 2x plus 4. Step 3 is actually the inverse trick. What do? To do inverses, you switch the x and y coordinate. In essence, you're going to make the independent dependent variable and the independent variable dependent variable. So, switch the x and y. So I get x is equal to 3y plus 1 over 2y plus 4. And then step number 4, you're supposed to solve for y. That turns it inside out. How would I solve for y if I got x equals 3y plus 1 over 2y plus 4? First thing you want to do is get rid of fractions. Multiply both sides by your common only denominator, 2y plus 4. This is going to give you x times 2y plus 4 is equal to, here it cancels, 3y plus 1. Next thing you want to do is distribute. And I put this problem on there because every year I see the same problem on the old final exam. They love find the inverse of this guy kind of a question here. So I make sure we always review it. I'm going to distribute. This gives me 2xy plus 4x is equal to 3y plus 1. Now solve for y. How do you solve for y? You juggle it. You get all the y terms on one side, all the non-y terms on the other. So I'm going to subtract 4x. I'm going to subtract 3y from both sides. That gives me 2xy minus 3y equals negative 4x plus 1. How many terms have y in it? 2 of them. Factor it out. You get 2x minus 3, y times 2x minus 3 equals negative 4x plus 1, and then divide. Y equals negative 4x plus 1 divided by 2x minus 3. The last thing, step number 5, is replace y with f inverse of x notation. So the answer is f inverse of x is equal to negative 4x plus 1 divided by 2x minus 3. There's my answer. With log properties, they're going to either ask you to expand or condense, combine. The way I look at log properties is this. It's the log properties or the Humpty Dumpty properties of mathematics here. What was the deal about Humpty Dumpty? What was your job? Humpty Dumpty had a great fall, right? You take your baseball bat and you bust that guy up into a bunch of pieces. Log properties. And then, what's all the king's horses, all the king's men, what are you supposed to do with Humpty Dumpty? Put him back together again. Exactly. So you got to combine log properties. So here is your log properties. Multiplication turns into addition. Division turns into subtraction. And powers get to go out front. So here we go. So this thing, I'm going to expand this guy. Multiplication is in the numerator. So this will be the log of 1,000 plus the log of x to the fourth plus the log of z. I don't do square roots. That's a half a power. Minus, because that y plus 5 squared is in the denominator, the log of y plus 5 squared. Multiplication turned into addition. Division turned into subtraction. And if it's in the denominator, you subtract it. If it's in the numerator, you add it. Where do powers get to go? Out front. So this is equal to the log of 1,000 plus 4 log of x plus 1/2 the log of z minus 2 log of y plus 5. Does that make sense? You got one more thing. Break down 1,000 for me, please. What exactly is 1,000? 10 cubed. Okay? So this is equal to the log of 10 cubed plus 4 log of x plus 1/2 log of z minus 2 log of y plus 5. But what is the base on this log right here understood to be? Understood to be a base 10. And we had a property that the log base a of a raised to the x cancels, and you're just left with the exponent. This base on 10, base 10 and this exponential are the same base, they're going to cancel. So you get your final answer of 3 plus 4 log of x plus 1/2 log of z minus 2 log of y plus 5. There's my answer. Again, using your log property. Does that make sense? Turn page. Here's the Humpty Dumpty problem again. But now Humpty Dumpty's got busted into a bunch of pieces. So in this chapter, what we're going to have to do is we're going to have to put Humpty Dumpty back together again. But when you check your log properties, here's the thing you've got to notice. To be able to combine logs, that means we're going to turn addition back into multiplication, subtraction back into division. You should notice that to be able to combine logs, the coefficient in front of the logs must be a 1 to be able to combine them. If you've got a number in front of the log, he's got to go back where he started from, which is the exponent, before you can combine them. So here we go. I want you to write 4 log of x plus 1/2 log z minus 2 log of y plus 3 plus the log of 8 as a single logarithm. Okay? All right, here's the thing. This thing's going to be equal to, if you got a coefficient in front of the log, you got to put it back where he came from. So this will be the log of x to the fourth plus the log of z to the 1/2 minus the log of y plus 3, that 2 goes back in the exponent squared, plus the log of 8. Does that make sense? Now you're going to turn it into one big log. Log understood to be base 10. They got to be the same base to be able to combine. Here's the deal. If it's positive, addition turns back into multiplication. Multiplication shows up in the numerator. If it's subtraction, subtraction turns into division. Division shows up in the denominator. Doesn't matter where their location is. Pay attention to the sign out front. This is understood to be positive, so when I combine these log base 10s of x to the fourth with the log base 10 of z to the half minus the log base 10 of y plus 3 squared plus the log base 10 of 8, if it's positive, it's going to show up in the numerator. So this is understood to be positive, so the x to the fourth shows up on top. This is plus, so z to the 1/2 shows up on top, turns into multiplication. Minus means that y plus 3 squared will show up in the denominator, because the subtraction turns into division. But this is plus. Plus turns into multiplication. Multiplication shows up in the numerator, 8. So now I would just make this thing look good, and this would be the log of 8 times x to the fourth times z to the 1/2 divided by y plus 3 squared. There's Humpty Dumpty put back together again. Does that make sense? Did I lose you guys anywhere? Questions? Okay. Now, here's the deal, and I'm going to let you guys go just a couple minutes early, but here's the deal. Very important. I want to kind of wait and do the log rules when we get back. But here's the real deal. When it comes to this material, we're about to jump into logarithms and exponentials and start to take a derivative of these guys, and we're going to be taking the limit of these guys and so forth and so on. 60% of calculus is algebra. You've got to know how to do the algebra on this stuff before you can actually manipulate the calculus part of this thing. So because of that, you've got to master the algebra. That's why we're spending so much time, and I even separated 3.1, 3.2, the algebra review from the limit, and then when I get finished up 3.2 here, we're going to be taking the derivative of these guys. And it's going to get convoluted, but as long as I can clean up the algebra first, it's going to make my world such a nicer place to be. You got to master the algebra properties of these things. Make sure you pick up the homework set, and I'll see you guys after hopefully a very safe spring break. See you guys on following Tuesday.